Okay. Questions? Yeah.
I don't exactly remember the problem, but I know we were doing the notebook. The question number 45 on top left, question 5.
Question 45. Let's see. Close. Okay. So 45, rank the substances from highest boiling point to lowest boiling point. Okay, so there's two things that go into boiling points or melting points. The first being the molecular weight of the molecule. The higher the molecular weight, the higher the boiling point's going to be, because that has to do with kinetic energy. So all things being equal, the molecule with the higher boiling point or higher molecular weight would have a higher boiling point. But if things aren't equal, then it's going to be a combination of those two, of molecular weight and intermolecular forces, with the stronger intermolecular force then being or leading to as long as the molecular weights are comparable, the higher intermolecular force is going to have a higher boiling point. So let's see, without looking at the answer key here, which ones are going to have the lowest boiling point? Three and four? Why did you say 3 and 4?
Because it's really carbon and hydrogen bonds.
So it's a hydrocarbon, which means that the best well, first of all, are 3 and 4 polar or nonpolar? Nonpolar? Do we all agree with that? Do we all know why? Well, because they're hydrocarbons, and so a carbon-hydrogen bond is a relatively non-polar covalent bond. And so in order to be polar, you need two things. You need a polar covalent bond, and then you need a molecular dipole moment. And so if you don't have polar covalent bonds, which carbon-hydrogen isn't, then you fail test one, so you're nonpolar. Okay, so those would be nonpolar, so the best they could have is dispersion forces. Okay. Then how do you decide between 3 and 4? Well, they did this 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Okay. They should have done 6 and 6. So it had the same molecular weight. But since they didn't, with hydrocarbons, and this will become for the reading on Friday, this is something that will be gone over. With hydrocarbons, if you have a straight chain, all the carbons attached in a continuous chain, that has a slightly higher boiling point than if they're branched off. And the reason for that is because if you have the carbon-hydrogen bonds in like a straight chain, what can happen is that the hydrogens, well, actually the molecules themselves will be able to fit. So you'd have, for instance, another alkane kind of fit here, and then another alkane fit underneath it, so that even though you have dispersion forces, you have a lot of surface area for those dispersion forces, which will make the boiling point higher, or the melting point higher as well. So if this carbon chain gets long enough, it'll be a solid at room temperature. And that's the type of hydrocarbon we would throw on the road as asphalt. So when you have a molecule like the one they gave you, which was like a sphere, then its kind of shape doesn't allow it to interact with a lot of surface area. So the more spherical the molecule, the less surface area there is. And dispersion forces are totally based on surface area. So the more surface area you have, even though it's a weak force, the more surface area will make it stronger overall. So if I'm looking at 3 and 4 here, I'm definitely choosing 3 as my lowest boiling point, or it's my lowest boiling point, and number 4 as next up on the chain. And I can't move things around the way you do. All I can do is show the responses, which I have no idea what that will show. And I can show the correct answer, but we can still work through the. So working through the remaining 2, do you have a gut instinct as to what you would rank as a higher boiling point, number 1 or number 2? Well, I got a better idea. We still have cards, right? And my phone is on its last legs. So I'll give you 3 choices. And I can't write on top hat the way I can a PowerPoint. Number 1 is A, higher boiling point. Okay, higher boiling point. Number 1 is A, number 2 is B, and if you're not quite sure, 3 is C. Okay. So if you can't make a judgment, so that way if you're like, I don't know, C. Let's see what we've got. We got 27 number 1s, 2 3s, and 7 beats me, which is perfectly fine. Would somebody like, if you chose if you were one of the 27 people that said 1, why did you choose 1?
Because of the hydrogen bonding.
Okay, so number 1 can undergo hydrogen bonding. Now, what is hydrogen bonding? So hydrogen bonding is when you have an atom attached to the hydrogen, and then that hydrogen is electrostatically attached to another atom. Okay, so this atom that's attached to the hydrogen is delta minus, delta plus, and then on the other side there is an atom that's delta minus as well. Okay. The X's can be what 3 elements? O, N, F. So X can be either O, N, or F. And so that means the X's here can be a combination of an O and an N, or an O and an F. And if not, if you have a question with any of this, you got to yell. Why is a hydrogen bond sort of a special, more stronger dipole-dipole bond? And that's simply because of the electrostatics. I mean, the Coulombic attraction between a plus minus or a delta plus and a delta minus is responsible for a very good chunk of chemistry. I joke sometimes, I'll say, well, if I meet a space alien, this does not endorse space alien theory, nor does it reject it, I suppose. But if a space alien came up to me and said, you're a chemist, tell me the biggest principle that chemistry is based on, I would say, first of all, why are you not nuking us? But I'd say, Coulombic attraction is probably responsible for a tremendous number of chemistry principles. and this is one of them. So it's the Coulombic attraction between the delta plus and the delta minus that makes the hydrogen bond. Why is it the strongest intermolecular force short of full-blown plus, full-blown minus? It's because the hydrogen has the greatest delta plus charge. How did it get that? By being bonded to one of the three most electronegative elements. So when you put those three electronegative elements, attach it to a hydrogen, they're very delta minus, and the hydrogen is as delta plus as it's going to get. And so that leads to a very strong Coulombic attraction. So that's why it's O, N, and F.
But also, isn't number 2, doesn't that also have oxygen atoms? So couldn't that also have hydrogen bonding?
So let's look at that. So the issue is, this is the definition of a hydrogen bond. It has to fit into that structure. So whenever we talk about the idea of forming hydrogen bonds, first of all, it said, ranking the substances. Well, what we have to realize is number 1 is a whole collection of number 1 molecules, and number 2 is a whole collection of number 2 molecules. So I'm going to take number 1s and have them attracted to number 1s and number 2s attracted to number 2s. Let's deal with number 2 first. So if you look at that, which is that functional group is actually called an ester. And it doesn't matter what the exact structure is. All of the hydrogens are attached in this molecule to carbons. None of the hydrogens are attached to an oxygen. Well, that's all we have here is oxygen. So all the hydrogens are attached to carbons. I cannot form a hydrogen bond between a hydrogen that's attached to a carbon and an oxygen. It's got to be oxygen, 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 nitrogen, oxygen, fluorine. Carbon cannot form a hydrogen bond. So any hydrogens that are bonded to carbon cannot be involved in hydrogen bonds. So this one doesn't have any hydrogen bonding. Now it does have some nice polar covalent bonds, like the carbon-oxygen bonds would have bond dipoles that look like that. And overall, it would have a net dipole moment, which would probably go somewhere like there. And so it would be a polar molecule. And so therefore, it would have dipole-dipole interactions. But with all the hydrogens being attached to carbon, it cannot be hydrogen bonding. So for this one, there's no hydrogens attached to an O, N, or F. The second one, though, which the key part is we have a nitrogen attached to a hydrogen. So this is called an amide, A-M-I-D-E. We'll learn next week about functional group names, chapter 2. So an amide has the hydrogen attached to nitrogen, so you could have a couple different types of hydrogen bonds. You could have it attached to the carbonyl of one molecule, and maybe this hydrogen would be attracted electrostatically to the nitrogen of maybe another amide. But either way, those NHs can be hydrogen bonded to another atom, an O or an N. So in this case, hydrogen bonding is possible. And so given approximately the same molecular weights, this one's going to have a higher boiling point. So it would probably, so as far as I can see from this answer, before I hit the button to show the answers and it's proven me wrong, which it may, but it's not wrong. Or I'm not wrong, it's wrong. And it shouldn't be in this case. So number 1, the highest boiling point would be number 1, then 2, then 4, and then 3 would be my guess. So let's see if that's correct. Okay. I have no idea what the I'm struggling with what the ACBD thing means. I get that the order is number 1, number 2, number 4, number 3, like it should be. But I have no idea why it says A, C, B, D. Right. I have no idea what that means. So I guess you ignore the A's, B's, C's, and D's, and you just go top to bottom. Okay. So if that's the case, that's the order. So the thing about the hydrogen bonding, that's just something we have to kind of remember is that, again, a hydrogen bond has to have an O and a F covalently bonded to the hydrogen and then electrostatically attracted to another O and a F. Any other atoms don't count.
On the topic of hydrogen bonds, there was a question, I think it was number 41, in section 1.3.2c, and it asked if it was a valid hydrogen bond, and just the formatting of how how it asked the question kind of confused me.
So number
how you would draw it as a regular Lewis dot structure, and then where the hydrogen bond would be.
So this was question number.
The one, the top.
This one, the one that's up.
Yeah.
The top one. Okay. Did I make that question up? I might have made that question up. So in terms of the formatting, what I'm showing is I'm showing a CH3 attached to an O attached to an F, and then on the other side it's a water molecule. So I couldn't draw and paste, so I had to type it in. So that question would look like this. There's a C with 3 H's, CH3, with an O and an H. So that's what's called methanol, that's wood alcohol. And then on the other side was a water molecule. So the question is that a legitimate hydrogen bond? Yes, because the hydrogen is covalently bonded to an O, N, or F, and it's electrostatically attracted to an O, N, or F.
In the question, the O in the wood alcohol had a dashed line to the H.
Yeah.
Does that indicate like the hydrogen bond if it's a dashed line?
I don't know. I'm pretty sure I wrote this question a year ago, which is why I'm only kind of sure. I think what I would have done is put an O with a single dash to the H, like the bottom one, where it says CH3 attached to an H, attached to water. And so in this case, in the bottom one, there's no hydrogen bond because it's CH to an O. Right. Yes. Well, you got that one right. Everybody got that one right. And nearly everybody got the other one right. So again, that's kind of how I showed it, but I had to type out the structure instead of drawing it. The day will come when I can just draw on the screen whenever I want, but it's not today. Okay. Right. What else? So that's what the hydrogen bond is. And so we have to go over that because we have to make sure we're all on the same page in terms of what can hydrogen bond and what can't hydrogen bond. And that will play an integral part of the physical properties. My best example is, so methanol is what's in it's probably in the blue fluid you put in for wiping your windshield off. So a little bit in there so it doesn't freeze in the tank in the middle of winter. So methanol is wood alcohol. You drink it, you go blind at best. Worse, you die. So it's not it's not that kind of alcohol. But if I opened up a bottle of alcohol, you'd have to come up really close to be able to smell it. It has a boiling point of like 80-ish degrees. It was one of the unknowns, so if you had a methanol in your experiment in lab, you know closer to the boiling point what it is. But if I make a single replacement of the oxygen with the sulfur, I now have what's called methane thiol. And skunks are locked and loaded with methane thiol. Actually, if you smell natural gas, natural gas is methane, it does not have a smell. The methane thiol that they add to it is why natural gas, if you have a natural gas leak, you can smell it. But methane thiol is what skunks have. And so if a skunk gets locked and loaded and decides it's aggravated enough, you can smell the skunk for, miles. And the reason is methanol has a hydrogen bond at a very high boiling point. Methane thiol is a gas at room temperature because it only has dipole-dipole interactions. And it has a low molecular weight with dipole-dipole interactions. That's why it's a gas at room temperature. Which part? So this has a boiling point of like 80 degrees or ish. Why? Because its strongest intermolecular force is hydrogen bonding. But since sulfur is not oxygen or nitrogen or fluorine, it is still a dipole moment, but the strongest intermolecular force with methane thiol is dipole-dipole. And so its boiling point is that it's a gas at room temperature. So one's a liquid, one's a gas. Why? The liquid has stronger intermolecular forces. Why? Because oxygen can form a hydrogen bond and sulfur can't. So that's a practical example. That's the practical example of a difference between oxygen and sulfur. Even though they're right underneath each other, or above or underneath each other on the periodic table, one hydrogen bonds, one doesn't. And that makes a huge difference in their compounds. Okay, anything else with polarity?
Could you give an example of drawing one of those like molecular moment problems with arrows?
Sure. Do you have a particular one in mind? Tetrahedral, trigonal, planar?
Not really.
So here's one that let's say that I gave you SO2, neutral molecule, I give you SO2 and I say, what's the strongest intermolecular forces that SO2 can undergo? Okay. So what would be that strongest intermolecular force? Now let's go through the steps. So I need help. What's the first step I should do? I heard it. Lewis dot structure. So let's write a Lewis dot structure for sulfur. So why don't you do that for a moment? And then you can tell me what the Lewis dot structure is for SO2. Sulfur and oxygen have 6 valence electrons. So both of them have 6 valence electrons. So what would the Lewis dot structure look like? Is it a question or is it the answer? The answer, okay, hold on. Okay, does everybody have a Lewis dot structure? Okay, you start with the oxygen. How many lone pairs on the oxygen?
2 sets of lone pairs.
2 sets of lone pairs and the bond to the sulfur. Okay, you had an answer too, right?
So one set of lone pairs
On
the sulfur, and then double bonded, and then the same on the other side for the oxygen.
Did we all get that? No? What did you get different?
I put a single bond between the second oxygen and the sulfur.
Okay, and what was over here?
Double bond.
Okay,
2 lone pairs of oxygen, 1 pair of sulfur, and 2 lone pairs.
somebody get the opposite where it's like this? Okay, so we have resonance structures. Beautiful. That's where we ended up on whatever day it was last time. Monday. It's been a rough morning. I'm still, my wallet is lost. That is, I had to go to the bank and it's like, if I didn't have my ID, they would not do anything for me. So don't lose everything. So I'm undocumented right now, which is going to be interesting as I try and drive my car home. Anyway, lab might be canceled tomorrow because I might be in jail. Who knows? Hopefully that's not going to happen, but it's a bad day. Okay, so we have 3 resonance structures here. The one thing I would say about the resonance structures here is that what we need to do is we need to rank them now. So how about formal charges? So let's work with the resonance structure that has probably that's the most stable according to our rules from Monday. So does the sulfur with the 2 double bonds have any non-zero formal charges? They're all zeros for that. Oxygen came with 6. It owns 1, 2, 3, 4, and then 1 each in the bond. 5, 6. That's a 0. Sulfur came with 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And oxygen. So they're all zeros. How about these 2 resonance structures over here? Any formal charges? On what?
Both of the
Sulfurs
sulfurs have a +1.
have a +1, and then the oxygen, that has a -1, and that one has a -1. And you'll learn after we write enough of these structures that an O with 3 lone pairs and a single bond always has a -1 formal charge. And one with a double bond and 2 lone pairs always has a 0 charge. So according to this, which one would be the most stable? Would be the one with the 2 double bonds, would be the most stable. If we had to write the hybrid, what we would have is we would have a delta plus charge on the sulfur and we would have 2 delta minus charges on the oxygens. But since these 2 kind of cancel each other out, I mean the average of those 2 is, well, the average of those 2, the average of all 3 is going to be this one. Now, I will just add an editorial comment here that if these are all legitimate resonance structures, then those atoms are in the same positions in each of those resonance structures. Why do I say that? Next step is what? After we get Lewis dot structure, I want to determine polarity, right? That was our goal. Number 2, what should I do? Put it into the Vesper geometry. So in this case, all 3 of these would have what geometry for sulfur, for the central atom? The sulfur would be trigonal planar. How did you know that? What's the hybridization of that sulfur? SP. 2 or 3? 2. So it's going to be sp2. It's got 1 lone pair and 2 sigma bonds. So that's sp3. Sorry. I'm sure that's what somebody else did. sp2. Right, it's sp2. 3 orbitals, sp2. Okay, so let's write that out then. We got our lone pairs. I got my double bonds down here. And so there's my trigonal planar geometry. Now, the best way to determine whether something's polar or not polar is to try and figure out if it's not polar. And it will not be polar if in our geometry, whether it's linear, trigonal planar, tetrahedral, if all of the positions, if all of those are the same, then they're all going to cancel each other out. If they're not the same, they won't cancel each other out. So if they cancel each other out, it's nonpolar. If they don't, it's polar. Okay? So that's what I'm looking at here. What I'm looking at here is a trigonal planar where I've got a lone pair and 2 oxygens. It is not symmetrical. And so therefore, my individual bond dipoles would look like that. You don't have bond dipoles for lone pairs. You just ignore them. Now, some general chemistry textbooks still put in that you put an arrow for the lone pairs. You don't. You only put them in for the bonds. Because here's what happens. The resulting bond dipole is going to be the vector sum of those 2 arrows. But if you don't like that, basically this part of the molecule is going to be delta minus, and this part of the molecule is going to be delta plus, because the delta minus is where the oxygens are. I guess what I should have done is I should have kept it in this structure and said, is SO2 polar or not? And if I would have asked you in that Lewis dot structure, you don't have to admit to this, but would you be tempted to say, oh, they're going like this, they're linear, they're going to cancel each other out, so it's not polar, right? That's why step 1, Lewis dot structure, step 2, Vesper geometry. You have to put it in the Vesper geometry. So if that's the case, clearly SO2 is polar. So this is now a polar molecule. And the question is, what does it mean to be a polar molecule? What it means to be a polar molecule is that you have an unequal distribution of electron density in your molecule. So you've got an area of delta plus and an area of delta minus, such that the delta plus end of one molecule, so they can line up so the delta plus ends will be attracted to the delta minus ends. And so in a dipole interaction, that's what it would look like. Now, if I had CCl4, which is called carbon tetrachloride, is carbon tetrachloride polar or nonpolar? There's two criteria for being polar. You have to have a polar covalent bond. Sulfur oxygen was a polar covalent bond. Is a carbon chlorine a polar covalent bond? In general, two atoms that aren't the same will be a polar covalent bond, except carbon and hydrogen. So carbon-chlorine bonds are polar covalent bonds. So check one. It has polar covalent bonds. Do the bond dipoles cancel, which would be nonpolar, or do they not cancel? Again, in a tetrahedron, they will cancel if all four positions are exactly the same. So in this case, all those chlorines will cancel themselves out. So that molecule will be all delta minus on its surface. And you could say, well, okay, but to be polar, you need an area of delta plus and an area of delta minus. If you only have delta minus on your surface, you're not polar. You have to have the delta plus and the delta minus, which means you have to have these a net dipole moment.
So you said that only if all four are exactly the same, when would it be these separate bonds?
They're not the same. They're not the same. So in a tetrahedron, all four atoms have to be exactly the same. If they're not, then it's going to be polar. So in this case, this is dichloromethane. Some of these molecules you may have in lab as unknowns. So this is called dichloromethane. Carbon tetrachloride is the one with 4 chlorines. And carbon tetrachloride is nonpolar. Dichloromethane would be, this one would actually be considered polar, with the delta minus part over here, and then the hydrogens over here with the delta plus.
Would another example be like if we use sulfur so it can have in its standard octet, and we did like sulfur and 4 chlorides, would you still say that that's polar? Shape.
Let's see. So sulfur with 4 chlorides. So chloride 1, chloride 2, chloride 3, chloride 4. So first of all, the sulfur would have what kind of geometry? It's got 4 sigma bonds and a lone pair. So that means it's going to look like this, right? It's going to be in that trigonal bipyramidal geometry. And so in this case, wherever the lone pair is, it's going to break up the symmetry. So if it was here, then the net dipole would be somewhere in that area. So this would be polar. It has, all 5 positions would have to be exactly the same in order for it to be nonpolar.
So a lone pair makes sense.
So lone pair always breaks up the symmetry, which is exactly what it did with the, which is exactly what it did in this SO2 case. If we had CO2, since carbon doesn't have lone pairs, it would be linear, and so in this case, these dipoles would cancel and CO2 is nonpolar. So carbon tetrachloride is an example of a nonpolar solvent, as is CO2 is nonpolar. But I'll just give you a practical example of that. Dry cleaning. What do they use in dry cleaning? Probably carbon tetrachloride. Although what they need to use in dry cleaning is a non-polar liquid to go through and remove the non-polar grease and dirt. But then the solvent evaporates, so it's dry. In the old days, if they did use carbon tetrachloride, the problem is carbon tetrachloride, if it escapes into the soil, it then goes down into the aquifer and when it gets in the drinking water, that's bad, because chlorinated solvents are bad. Somewhere in the state of Tennessee, I believe, there's like 1 million gallons of of carbon tetrachloride floating around in the dirt that hasn't hit an aquifer yet, because it escaped from something. So there's a 1 million gallons is it's a little bit or a lot, but it's in the soil, and if I had well water, or if I had a city that was pumping out of that aquifer, hopefully it never gets into that. So carbon tet's kind of out as a dry cleaning solvent. You say, but CO2 is a gas. Not if you compress it to really high pressures, then it becomes a liquid. So then you can take your CO2 liquid, pass it through your clothes, and then on the other side, either let it expand, and then all the dirt falls out, then you recompress the gas and use it again. So CO2 can be used to dry clean. It can be used to like extract oils from flowers and stuff like that too. You buy essential oils, there's always the CO2 extracted that chemically are different than the steam distilled ones. At least that's what I've found. It's like, wow, this one's really different. Why? Oh, it's CO2 extracted. And I don't smell them, so I don't know. We'll come to that stuff later on in lab. So anyway, they're nonpolar. So they make perfect dry cleaning solvents. Right. And CO2 is bad, but if we keep it from going into the atmosphere, and we're not making new CO2, and we're just compressing it and using it over and over again, it's probably not that bad. So that's what I mean by the symmetry. If it's symmetrical, it's nonpolar. If it's not symmetrical, it's going to be polar. So that's how we look at that. So let's see, I know we did this where we were saying which one of these was more stable than the other, but isn't that kind of where we left off on Monday too? Was we were going to do the OCN and determine which one's more and less stable. Does anybody have a question before we do that kind of quickly? So I'll sketch it out. OCN, right? That's what we were doing, was OCN. There was OCN resonance structure number 1. Here is OCN resonance structure number 2. Here is OCN resonance structure number 3. If I remember correctly, this is -1, that's -1, this is -2, and that's +1. So there were our 3 structures that we developed on Monday. And so we had A, we had B, and we had C. And so if we're ranking them, we had our rules, which our rules were number 1, completed octets. They all pass. Rule number 1B, 0 formal charges better than any non-zero formal charges. Well, they all fail because this was an OCN minus ion, so it's got to have formal charges. So then rule number 2 is small numbers of charges and small charges versus large numbers of charges and large numbers. So that eliminates which one is the least substituted, or these stable. C. So C was automatically the least stable. And then we're down to A and B. Which one is more stable? Oh, I think we need to use the cards. Do you need a card? I don't have an extra card. You'll just have to psychically give it to me. So A is A, B is B. I suppose you could have C, meaning they're the same, but they're not going to be the same. So that's either A or B. Which one is the most stable? The most stable A or B? Okay. We have 29 to 3 to 5, and the 29, what was the 29? The 29 was B. B being the most stable. So why is B the most stable? Well, rule number 3 says that we should match up the charges with the electronegativities. And what does that mean? That means that if you have a choice between a -1 nitrogen and a -1 oxygen, which is the difference here between A and B, the more electronegative element should get the negative charge, and so that more electronegative element is oxygen. So if we're going to write the hybrid of this, I would say let's write the hybrid of A and B, which I think that's probably exactly where we were at, in exactly the same place we were on Monday. So we average charges, we average bonds. So I'm only going to average A and B here. So oxygen in A is 0 formal charge minus 1. What's the average? You could say like -0.5, but that assumes that they're 50-50 in terms of their stability. They're equal stability, and they're not, because we just said B was more stable. Do I care about an exact number? No. If I do, then I got to go to the computer in order to figure that out. So I know that oxygen is somewhere between 0 and -1. So how am I going to designate that? Delta minus. Some or partial negative charge. So the oxygen is delta minus. The carbon, 0, 0, average, 0. Nitrogen, -1, 0, average, delta minus. So just from the charge standpoint, I know the charge is -1 overall. That means the charge on oxygen and nitrogen must add up to -1, but who has the greater negative charge? Oxygen. Why? It's more electronegative. Okay, we average bonds. So OC bond, double single. In between a double and a single bond is a partial double. Nitrogen, triple double. In between a triple bond and a double bond. So we use the dotted lines to indicate partial bonds. We use the delta symbols to indicate partial charges. And so that would be our resonance hybrid. So lengthwise, the CO bond is somewhere between a long CO single bond and a shorter CO double bond. It's somewhere in between. Okay, so I said I was going to have take-home practice problems for you today. I do not. I will have those for you on Friday, but I will go in and clean up the website, so if you have any questions. I also, somebody asked, how do you see the narrated answer keys? And I failed miserably this morning because there's a couple different ways to do it, so I'm going to record a video and I'll put online exactly how you can see those, but there's like one of 3 different methods. So I'll show you that. If you have any questions, I know there's one question on Piazza that I haven't gotten to. If you have any questions, throw them up on there or email me. Otherwise, on Friday, we'll go through whatever you have. Friday is kind of a catch-up day, so if you're looking through going, well, this stuff's pretty straightforward, that's okay, because Friday I think I have planned we can do some more of these problems and we can talk about whatever it is that we didn't talk about today. Hybridization, if you wanted to sketch how to sketch out hybrids. Okay? So read through the assignment and I'll see you on Friday.